thank you for your introduction. So in this talk, I'm going to present a work that we did about multi-cloud orchestration. In particular, we designed an algorithm to reorchestrate microservices in order to minimize the deployment costs, while at the same time preserving the service continuity. So before diving into the proposed solution, we'll briefly introduce you what is a multi-cloud system and why cost minimization is important. So from a service provider perspective, multi-cloud refers to the utilization of computational resources, often in the form of virtual nodes, that are offered by different cloud providers to deploy their microservice-based application. The main advantage of this cloud model is that it improves the scaling capability of the application, as the number of virtual nodes can be dynamically adjusted based on their resource requirement. However, there are two main problems that need to be taken into account when relying on multi-cloud. The first one is that the network latency between virtual nodes is usually non-negligible, as the physical infrastructure of the various cloud provider is geographically distributed between different zones. And second, which is the most important one, is that you are paying for that virtual nodes. So it is essential to improve the resource utilization efficiency of your deployment in order to mitigate the economic costs associated. So in this context, these challenges that I just mentioned are usually handled throughout proper microservice orchestration that makes sure that the various microservices are deployed based on their resource and latency requirement on a suitable number of virtual nodes. In this context, the state-of-the-art proposes several orchestration schemes where the main idea is to jointly optimize the cost and the quality of services of the application using different approaches. For example, heuristic algorithm, optimization, machine learning, and so on and so forth, or under different assumptions of the cost model. Some use the resource utilization, other the number of nodes, other one the network bandwidth exchange between different regions. So regardless of the assumption, however, the main limitation of this work is that the solution assumes a static deploy configuration. And most importantly, which is a direct consequence, they ignore the performances of this solution when you try to reorchestrate your workloads. As a matter of fact, why this is important? Because usually the deployment requirement of applications may change over time for a variety of reasons. For example, you want to rescale the resources to accommodate different workload conditions. You want to write new features. You want to deploy new application to accommodate different use cases, or vice versa. You want to terminate some application because, for example, the task has ended. So this dynamicity on the long run increases the resource fragmentation and deteriorates the original cost efficiency that was computed by the orchestration scheme. So for this reason, it is important periodically to reorchestrate the deployed microservices. That means reallocating them on a different number of virtual nodes in order to restore the deployment cost efficiency while also preserving, of course, the quality of service requirement. So the point is, why cannot use the same reorchestration algorithm that I already used for the first deployment? So in principle, you can do that. In practice, you need to account how Kubernetes, which is the facto the default orchestrator that is used by the industry, how Kubernetes handle containers, which are basically our microservices. As a matter of fact, there are two types of deployment strategy. The first one is called recreate approach. Basically, if you want to update a microservices that is a container or a pod, you terminate the instance and you redeploy it as new with a new requirement. This is completely fine. As a matter of fact, you are erasing your deployment, you're starting from scratch, so you can achieve the same cost efficiency and the satisfaction of the various quality of service constraints that you had previously. However, you introduce disruption because your application is not working, so you have some downtime, and for some use case might be tolerable, for other cannot be tolerable. So in the end, you might perform this sort of operation frequently. So it is not a good practice. The alternative, which is actually the default way Kubernetes to update pods, is using a rolling update strategy. That means we first deploy the pod with the new requirements, and then we shut down the old instance. In this case, we have solved the problem of service disruption because the pod is still working. We redirect all the requests to the new instance, so we are fine, basically. However, if we look in the perspective of the cost saving and the quality of service constraint satisfaction, here we have some sort of inefficiency. I will explain you later why in the next slide. But basically, the problem is that we are using for a temporary amount of time more resources than what actually we need. And if you do not account for this dynamic in your orchestration algorithm, you have some losses. So the idea is that we have this solution with this deployment strategy. Can we design an orchestration scheme that keep the benefit of all of that? So basically, we want to be cost effective, we want to preserve QoS, but most importantly, we want to ensure service continuity. So to better understand this point, I will show this example that I hope convince you what is the difference between recreate and rolling update and why it is important to account when you design a orchestration algorithm. So assume you have this application, where of course it is not a practical case, but it's reasonable, is quite a real world scenario. So basically you have this application that is deployed on 2 regions, for example, where Cloud B offers some nodes that are more costly than Cloud A. So in principle, if you would like to use Cloud A region because it's cheaper. For some reason, you want to downscale your application because you want to accommodate a different workload condition. So you change the CPU requirement of some pods, and you trigger a rescheduling of all the deployment in order to see if you can fit the resources in a lower amount of node and possibly save some money. If you do that with the recreate approach, what happens is that the Kubernetes schedule, the default one, use the recreate strategy. So basically, assume that now we want to reschedule everything. So it means that we erase our pod and we deploy them from scratch. And this is quite intuitive. It's easy to achieve, and we can achieve that performance. So you see that now we can repack our microservices in a lower amount of node. So node 3 is empty, and if there is a cluster autoscaler, that virtual node can be terminated. So basically, we have some economic saving. However, here, as I mentioned before, I'm introducing some disruption, so it's not a good solution. What if we try to with a rolling update strategy? It means that we want to move each pod by first deploying the new instance and then shut down the old replica. The point here is that we cannot longer have a simultaneous deployment because, of course, we need basically double of the resources that we needed beforehand. So basically, we are mostly constrained to do it one at a time, unless using more nodes temporarily. But assume that we want to reschedule each pod one at a time, so we need to enforce some sort of order of this pod. And I start by default using the pod ID, for example, starting from node pod 1 to pod 5. If I follow this order, basically what happens is that now pod 1 is scheduled on node 3 because it has not other opportunity. And if I keep this procedure, so I end up with something like this, you see that even though I try to minimize the number of nodes because I try to repack the microservice on the most loaded node, I end up in the same situation as before. So basically, I have no economic saving, and basically the rescheduling was basically worthless. The point is, however, that we now introduce no server disruption, but as I mentioned, the cost efficiency is the same. So the point is, can we try to find a rescheduling algorithm, so an orchestration that try to make the order a bit smarter in such a way that we can still have the same cost benefit of the recreate approach? For example, here we design this algorithm that reschedule pods in this order. So I start, for example, on pod 2, and then I go ahead with pod 1 and so on and so forth. You can trust me, you can check the order, but basically what happens is something like this. So I have the same pod, I just modified the scheduling order and the node assignment, and I was able to achieve the same performance in terms of cost as the recreate approach. As you can see here, node 3 is empty, so basically can be terminated and have the same economic savings as the recreate approach. So basically, that's the core of our solution. We try to design a smarter rescheduling algorithm that try to take advantage of the rolling update to ensure service continuity while maintaining cost efficiency, and also the QoS preservation that I'll just introduce in the next slide. So how we approach this problem? Basically, we rely on optimization approach first. So basically, our objective is cost minimization. So basically, I will just give you a hint of how the mathematical formulation has been designed. But basically, the objective function is the sum of the cost associated to each virtual node. Keep in mind here that if a virtual node is active, it means that it has some pod allocated on it. So we're paying the full price. And we assume that if we manage to remove some pods on some node, there is a cluster autoscaler that basically terminates that virtual machine, and that we are sure that basically we are not paying money for that node. So the idea is that to modify the allocation of the pod in such a way to reduce the number of nodes, of virtual nodes. How we encoded the rolling update constraint here, we use it basically we enforce it our order. Basically, we try to satisfy two conditions. The first one is that we need to account for the fact that when I'm using rolling update, there is a brief amount of time in which the same pod is coexisting, so the old replica and the new updated version. And also, we need to track basically the load variation in each node that changes during the rescheduling phase, because now when we are moving pod from one node to the other, the capacity can either increase, the load can either increase or decrease. This is quite important to take advantage of optimization and try to reduce the number of virtual machines in the end. And third one, which is most reasonable, is the most intuitive, is the quality of service constraint that we translated in terms of latency requirement. So we assume that we want to collocate pod in the same region if they have some tight latency requirement. So basically, it's an on-off constraint. So if we assume that between each different region that is a different cloud provider, we have some latency. If this latency is too high and the pod latency might be affected, so we enforce that the two pods must be collocated in the same region. If we compute the solution with an optimizer, we end up something like a rescheduling order, so the node assignment, and when to perform that node assignment, so the rescheduling slot. And the benefit is that we minimize the cost. We have no service disruption because by design, we're using rolling update. And the QoS is preserved because we are enforcing the collocation of different microservices when needed, of course. The point is that this formulation is NPR. It means that it's not computationally efficient. So for a high number of pods, the node is untractable. So we need to find the heuristic so that approximate the optimal solution. Of course, we'll pay a price in terms of performance, but we'll gain a benefit in terms of computational complexity. That's what matters. And how we approach this. So basically, to design a heuristic, we need to replicate somehow how the optimal formulation works. So the optimal formulation does two things at the same time. Is the node assignment. That means it tries to minimize the cost by repacking nodes on the lower amount of node, and also to enforce the collocation of microservices, that is the quality of service requirement. And the second step is try to decide when to perform this sort of reassignment, which is the service continuity. So instead to do this at the same time, we separated the two tasks and we did one after the other. So first, we addressed the node assignment. So we pretend that our cluster is empty, and we just take care to repacking microservices in a lower amount of node on the cheapest node, while also ensuring that the collocation requirements are satisfied. And then in the next phase, we try to take care of how we can reorder this sort of reassignment in such a way that we don't need to turn off any pod, because we need to exploit the capacity in each node to accommodate the old replica of the microservice, the new replica of the microservices, and then taking account that that replica will be turned off in the next time slot. So basically, we designed a rescheduling order algorithm that try to enforce this sort of rolling update procedure. The point is this phase, since we are doing this step separately, we cannot have an optimal performance, so we need to pay a price. And in some scenario, we still need to introduce some disruption. It means that we need to terminate some pods in order to make sure that the reordering is feasible, but we'll show in the result that this penalty that we pay is very small, so it's worth the trade-off. Now I will present, since this is the main idea, I will present the result of this approach. So we simulated the environment. So basically, we're not using real Kubernetes, but we also have a demo about that, but these are simulated performance. And we assumed a scenario in which basically we have several microservices, and a percentage of that microservice has been downscaled by 50%. This number has been decided according to the Alibaba cluster trace program that provides some traces about the cluster utilization of Alibaba provider. So somehow we are consider a realistic scenario. And we assess the performance as we increase the number of rescheduling microservices to see how our algorithm behave in this scenario. Our benchmark is Kubernetes, and what we try to do is we implement the Kubernetes scheduling logic in the following way. So Kubernetes has different way to handle this sort of scheduling procedure. For example, if you want to repack microservices on the least amount of node, which is our node, you can, it has a plugin that has most resource fit. We try to do what I just mentioned. Also, if you want to make sure that your node is likely to end up in some node. In our scenario, the cheapest node is the node affinity, so you give priority to a node with a certain weight. And also, if you want to make sure that we somehow enforce the collocation, we have this other plugin that enforce the pod affinity. Means that if two pods have high affinity, it's likely that they end up on the same node. So we make, heuristically, we are sure that at least they try to be collocated. And so we implement this logic and we test it with the recreate strategy. That means that we erase everything and we redeploy. And with the ironic update strategy, that means we do one pod at a time. The metrics are the following. So the deployment cost is basically the cost of a deployment, how much money we pay for our virtual nodes. The second one, it is disruption cost. That means how many microservices we need to turn off in order to accomplish our rescheduling. And finally, it is the QoS violation probability. That basically we measure how many constraint we violated after the rescheduling phase. It means that if a certain set of pods were meant on the same region and after the rescheduling are on different region, this is not good. It is a QoS violation, so we count it as a violation that need to increase the inefficiency of the algorithm. Now I will try you some numerical results. So in this plot here, what you see what I just anticipated, but basically here we have 50 microservices. We assume to have 4 cloud region. And what you see here basically on the x-axis is the number of rescheduled microservices that increase. So basically we start from 10 that are the one that we originally downscaled. And then we still increase the number of rescheduled microservices up to the maximum now, which is 50, to see how this approach behaves if we give more degree of freedom, because the idea is that we can reschedule pods on a lower amount of node. So if we increase the number of pods, possibly the algorithm might perform better. And on the on the y-axis, we see the cost, which is normalized, but basically the lower the number, the lower is the cost. And we see the several benchmarks and several schemes. So the optimal one is the blue curve and to perform best by design, which is based on optimization. This is quite close to recreate approach, which makes sense actually, because recreate approaches start from erase everything. So by deploying everything from scratch, it's easier to accommodate microservices in a lower amount of node. The heuristic here, you see that the orange curve pays some penalty, as you circled in the red circle. But this is a price that we need to pay with the fact that we are doing the step one after the other, but still it is close enough to the optimal one. And actually the ironic update, which is the one that usually is designed by default by Kubernetes, performs quite poorly. And this is due to the fact that indeed there is no order enforcement, so microservices can be scattered everywhere due to the fact that they do not account that you have the old replica to take care of before design where to deploy your new pods. If we now look at the disruption cost instead, which is how many microservices I need to shut down, here on the x-axis I have the same number of, always the same number of scheduled microservices, and on the y-axis is the number of turned-out microservices. Here, the recreate approach by design, since we erase everything from scratch every time, as you can see, it's skyrocket because it's directly proportional to the number of rescheduled microservices, so this is really bad. Instead of the optimal one and the rolling update one, by design, they use the rolling update approach, so basically they are close to 0. And actually, our heuristic, as you can see, are the orange solid line is quite close to the optimal approach. So basically, they shut down 1, 2 microservices, and this is the penalty that I mentioned beforehand. And the other heuristic that you see, this is a orange dot line, is basically an heuristic where we randomize the order to assess that our order algorithm is actually meaningful. So basically, we're saying, okay, the way we design the order actually has an impact on the disruption performance, and that's the quantification of this metric. And finally, I will show you now instead the QoS violation probability. Here, on the x-axis is always the number of scheduled microservices, and then the y-axis the probability that basically 2 microservices get separated on different regions. As you can see here, the rolling update performs quite poorly because it has many metrics to account for, and also since the class is already overloaded, it's difficult to find enough room to move pods altogether if they're meant to be on the same region. And you see all this efficiency. Also, by simulation, we started from an original starting point that was quite challenging to maintain the QS requirement in order to stress the algorithm. And you can see here we have really high numbers. So basically, the cluster is not manageable. Is basically the probability is too high. So basically, your applications are not working. Same for the recreate approach. Whereas the heuristic with the optimal basically achieve close to zero because the optimal, because it's optimization based, so enforce the requirement. Whereas the heuristic one, basically we employed a really conservative approach that try first to satisfy the quality of service requirement, and then take care to minimize the cost. And you see that this penalty is translated in the cost that in the deployment cost graph that I showed beforehand, because that gap you see from the optimal is due to the fact that we are trying to first enforcing the QS requirement. As a final result, I show you now the computational complexity as basically the optimal solution. This is the blue curve, is untractable. As you can see, it takes a very long time, almost an hour for 50 microservices. So basically, is not practical at all. Whereas the heuristic, we see that we managed to really decrease the performance of the computational time requirement. So it is basically practical. It's still slightly higher than a recreate and only calculated logic, but still completely manageable from a practical perspective. So this concludes the presentation. Basically, the key message is that the cost minimization in multi-cloud is important because habilitate the cloud model, the multi-cloud model. But in order to take full amounts of that, we really need to make sure we are cost efficient. To be cost efficient, we need to reorchestrate our deployment. But to reorchestrate our deployment, we need to take care of how Kubernetes works. And to do that, we need to make sure that we not do no disruption and we still satisfy the quality of service requirement. And to do that, we need to design an algorithm that is aware of this logic, the running capability logic, and make sure we optimize the rescheduling order and assignment in order to achieve this cost efficiency. As a future work, we are trying to improve this approach. For example, we want to minimize now the number of requested microservices because right now you can move any pod in our cluster. So we want to make sure that it reschedule only the just amount that is needed to minimize the cost. Also, we want to improve the rescheduling latency. It means that if we possibly want to simultaneously reschedule more pods in order to reduce the time that the rescheduling phase lasts. And finally, all of that actually will be integrated within Kubernetes scheduler to make sure that actually things work in practice. So our idea is to finalize this work on a practical Kubernetes scheduler plugin that actually is doing what it was designed for. And here, if you want to know more about this work, we have a paper published, and this is the link of our work. And with this, I've concluded my presentation. Thank you for your attention.